This is the third video on two-body central force problems. So let's once again summarize what we've done. We have two bodies that are interacting through a central force that is conservative. And we can write them down the Lagrangian on this form, including kinetic energy and potential energy, and with proper change of variables. So we go into this relative coordinates and center of mass coordinates. We can write this Lagrangian as a sum of a relative Lagrangian, which depends only on little r, and a center of mass Lagrangian, which depends only on r, or actually only on r dot, capital R dot. This is now essentially a six-dimensional problem, right? Because we have two particles at position r1 and r2, each of which has three spatial dimensions. We then show that in the center of mass frame we are inertial, so we can actually stick to looking at only what's happening in the relative motion frame, and then we get this reduced Lagrangian here, which depends only on little r. So we've now taken a 6D problem, reduced it to a three-dimensional problem, and the reason we were able to do that is essentially due to conservation of momentum. Which leads to the center of mass moving at a constant velocity. Then we also showed that using that conservation of angular momentum, we can show that the this variable here r is actually moving only in a plane, and therefore the problem reduces to a two-dimensional problem. This is now due to conservation of angular momentum. And with a little bit more work, we could find an expression for phi dot in terms of r. This is also due to conservation of angular momentum, and that reduces us then to this equation of motion. So mu, which is the reduced mass, times r double dot, it's just mass times acceleration, equals minus the dr of u effective, which consists of the real potential plus this centrifugal potential here. We've now reduced the problem to a 1D problem. And this last reduction in complexity also came courtesy of conservation of angular momentum. Okay, so we have now simplified the problem sufficiently that we can actually try and solve it. But before we do that, let's take a look at this effective potential here that we constructed. And specifically, let's look at the example of a comet around the sun. So let's say that we have a sun here. It's the sun. And a comet. And of course, you know, the tail of a comet is always pointing away from the sun, even if the velocity is pointing in some other direction. So this would then be maybe m1, and this is m2. And the line connecting the two has length r. So in this type of situation, we have a gravitational potential energy, which depends on r, and it's minus capital G m1 m2 divided by r. Now, using our effective potential here, that would therefore be equal to, minus gm1 m2 divided by r plus this term, L squared, that's the angular momentum magnitude, divided by 2 mu r squared. If you plot that, it looks something like this, depending on what value for L you're using, right? So if you have a large value for L, then you get like L3 here. This red one corresponds to a smaller value for L. Here we have L2, L1 for the even smaller value of L. And if L is equal to 0, well, then this term goes away entirely, and then you diverge towards negative potential values when R becomes really small. This shouldn't say X here, this should say R, of course. Okay, so we have a few points here that are interesting. Because this potential now consists of a sum of a negative and a positive term that go to zero at different speed as R increases. You have this point here, R0, where the potential is at its minimum. And depending on what value we have for the energy, the behavior is going to be different. So for instance, if we take an energy here which is less than 0, that means that the motion is confined between two turning points. Maybe roughly located here and here. So here's a minimum R. That's the point of closest approach. And here's a maximum R. On the other hand, if E is greater than 0, then the distance between the two objects, R, could be infinitely large. So because, and this comes about because the potential, the effective potential, goes to 0 at infinity. So we can use the sign of the energy to tell us whether the system is bound or not. And when I say bound, I mean that there's a maximum distance by which the two objects are separated ever. In an unbound system, the two objects can be infinitely far apart. The other thing that we can see is that for, just looking at this, is that for large values of R, the gravitational term here dominates, whereas for small r, the centrifugal term here dominates. And then for R small, then we have the centrifugal term dominates. Okay. And this latter thing is true as long as we don't have L equals 0. If we have L equals 0, then there is no angular momentum in the system. Essentially, the two objects are headed for a collision course, and the potential energy, the effective potential energy, just becomes more and more negative as the distance between the particles, or the planets, or comets, or whatever it is, becomes smaller and smaller. Now let's take a look at the equation of motion again. So just to remind you, it was mu r double dot equals minus ddr of u effective. Essentially, this is the mass times the acceleration equals the force in the radial direction. Although we know, as we've said already, that this force includes the centrifugal force. So what we're going to do now is I'm going to recast this in a slightly different form. I'm going to begin by multiplying this equation by an r dot. Let's draw a line here to make sure that this is well separated. Then we get mu r double dot r dot equals minus r dot. Okay. Now, because this is a single variable problem, this is essentially, we can use the chain rule. We can say this is dr dt times ddr of u effective. That's the same as with the minus sign. That's the same as minus ddt of u effective. We can also see that on this side, this can also be written as a time derivative. Right? We can say that this is what we get if we take ddt of mu, or 1/2 mu r dot squared. And that's therefore equal to minus ddt of U effective of R. So we can put these two over on one side of the equation and then integrate. We will then find that we have 1/2 mu R dot squared plus U effective of R equals a constant. Let's remind ourselves now what U effective is one more time. U effective is the gravitational potential in this case, plus L squared divided by 2 mu R squared. L here is the total angular momentum, the magnitude of the angular momentum, and we know that L is mu R squared phi dot. So that means that L squared equals mu squared R4 phi dot squared. And this in turn means that L squared divided by 2 mu R squared is going to be equal to 1/2 mu R squared phi dot squared, or if you like, 1/2 mu times the square of R phi dot. R phi dot is the velocity in the phi direction. So this is just 1/2 mu times v phi squared. In other words, this is the kinetic energy in the phi hat direction. In other words, it's the tangential kinetic energy. So if you look here at the comet, the kinetic energy we just wrote down is the kinetic energy associated with motion in the phi hat direction. So not back and forth along R, but in the phi direction like that. So what that means, let's put this in a little box over here. What this means is that this equation that we wrote down earlier, we can now rewrite like this. So this is basically saying that the radial kinetic energy here plus the tangential kinetic energy plus the gravitational potential energy, that's equal to a constant. So this statement is just a statement of energy conservation. We can also look at it from the point of view of the reduced variables, that is, we have only R to worry about. Then this is just the kinetic energy. And then this entire portion is the effective potential energy. And that's equal to a constant. So whether you count this piece as part of the kinetic energy and the potential energy is really just a bookkeeping question. What makes it simpler to use this picture, we have kinetic energy plus effective potential energy, is that now we can do the problem in just one variable, R. And no matter how you view it though, the constant here that is just a total energy E. And like we saw earlier here, the sign of that tells you what kind of orbit we have. So if we have energy less than 0, then we have a bound orbit. If the energy is greater than 0, then it's unbound. Which means that R can be infinitely large. E can also be equal to, at its minimum, U effective at R naught, and remember how we define that, that's the point where the potential energy, the effective potential energy, is at its minimum. So if that happens, well, then we can have, then R is fixed, right? R if this is our total energy right here, then r can neither increase nor decrease, and we have circular orbits, because r changes not at all over time. So we have no radial kinetic energy in that case, right? Because the total energy equals U effective. No radial kinetic energy means circular orbits. Now let's assume for a second that the total energy is less than 0. So if that's the case, then what we have is that r changes between a minimum and a maximum. Right? The orbit is bound. And also, we have that phi increases monotonically. The reason we can say that is, again, due to this definition here, right? R is always positive. So if I write down that phi dot equals L over mu r squared, then we know that L doesn't change sign, it's a constant. Mu is a constant, and R is always positive. So that means that phi dot always has the same sign. That means that phi increases monotonically. Okay, so we can say that. And we're going to use that here in 1 second. Because what we're going to study now is the equation of motion. Now, we have already found the equation of motion in principle. It is that mu times r double dot equals minus the u effective dr. And that gives us the motion. But what we are interested in are the orbits. Okay. And that is essentially r as a function of phi, which then can be dependent on t. Now, these aren't necessarily closed. I should mention, it turns out that those are closed only if the force varies as 1 over r squared. So that's an inverse square law force. Or if F varies as R, or minus R, as is the case in the harmonic oscillator. If you don't have that, you don't have closed orbits. But these are the two cases we're going to work with, so we can assume that the orbits are closed. So in any case, we are interested in finding the orbits r of phi, and phi will then be the variable that depends on time. So to do that, we'll do a few mathematical manipulations here. The first thing will be that we will have it. This is U effective. I'm going to bring this down here just to keep it on hand. So I'm going to write this on force form. So we have that mu of r double dot equals F of r plus L squared divided by mu r cubed. So L squared mu r cubed, that's just the derivative of this with respect to r with a minus sign. And F of r, that's just minus du dr. Right, that's the force that corresponds to the actual potential. I'm now going to introduce a new variable. Turns out to be a bit more convenient for a bit here. I'm going to introduce u, which is just equal to 1 over r, right? Which means, of course, that r equals 1 over u. That's one of the things I'm going to do. The other things I'm going to do is I'm going to rewrite the derivative with respect to time. Since in this case we're dealing with a single variable problem r, which we are saying depends on t only through the variable phi, we can just apply the chain rule like this. And here it's convenient that phi increases monotonically. This has a given sign, positive or negative. So that is then equal to phi dot d d phi and then we make the change of variables here. So then we can see that r dot and these cancel. And then we also need our double dot. So those are our two results. Those I'm going to apply to this equation here and see what we get. So we take this radial equation of motion and just plug things in, and we get then of course we note that Q is only a function of R, so slightly simpler we can just write it as, and by simplifying a little bit, we can for instance note that two of the U's here go away. So that's the equation of motion that we need to solve. It's a little simpler than this one, it turns out, and it also gives you the orbit directly. And that's what we're going to undertake in the next video.